Assalamualaikum and hello everyone. Welcome back to our class on Introduction to Machine Learning. I'm Dr. Maharani Abu Bakar, the instructor of this course. Today, we're going to explore one of the most powerful classification methods. It's called the Support Vector Machine or SVM. And this topic is actually part of our series lecture Supervised Machine Learning. Okay, so before we going further to determine a good hyperplane, so better we understand first some concepts. Okay, first we have margin. So what is margin? So the margin refers to the distance between the closest data points from each class. So this is the margin, okay? From each class to the separating hyperplane. Okay, so this is the margin. This one, Okay, so do not imagine like hyperplane only one line. So this is one line, but it has width. Okay, so it says like this. So it has the width. This one is called the margin. Alright. Okay, so we have support vector. So that's why it's called the support or support vectors, right? The support vector. What is it? Alright. Okay, before that, we have a fact here. Which kind of margin that we need actually? So here is called the best hyperplanes. Okay, is the one that maximizes this margin. So we want the maximum margin. Okay, so the maximum margin means the good hyperplane. Alright, now let's move to the support vectors. Okay, what is it actually? So the data points that lie closest to the margin. So this is data point, right? There are many data points. So there are certain data points that are very close to the margin, okay, and these data points influence the position of the hyperplanes. That one is called the support vectors. So not many vectors that we can consider as the support vector. These are only certain points. As long as the support vectors, the points or the data points close to the margin here. Okay, so for instance, like this point, very close, right? We can take this one as well, right? This one, okay, depending us how many vectors that we want to include to determine some parameters involving later in the calculation. Okay, so I just want to say this one is called the support vectors. So we have to find the data points which is very close to the hyperplanes. So this is an example, right? Okay, now we talk about the classification using a good hyperplane which can classify correctly the data points into two classes. Alright. Okay, so in the binary classification problem, so we named our problem is the binary classification problem because the hyperplanes exactly separates the spaces into two classes. Okay, it's called the binary problem. Alright, binary classification problem. So in the binary classification problem, we aim to find a hyperplane that separates the two classes with the largest possible margin. Okay, with the largest possible margin. So just like we explained before, since we have data points, okay, and then we have data point over here. So we want to maximize this margin. Why? Because we want to make these points close to the margin. We want to find how wide I can draw the margin, the hyperplanes, okay, such that many data points can get closer to the hyperplane. So that's the aim. Alright, mathematically, okay, we define this with a decision functions. So it's called the decision function, okay, which includes the weight vector W and the bias B. Okay, so we have decision function, okay, with the formula as W transpose X plus B equals to 0, where W is the bias, the weights, alright, and B is the bias, and X is the data point. So this one is called the decision function, right? Alright, so this decision function helps us to define which sides of the boundary data points lies. Okay, so if, as I said before, right, if W transpose X plus B is greater than 0, for instance, so the data points is lies upper the hyperplane. If this is less than 0, then is below to the hyperplane, right? So now let's have a look at this data point. For instance, we have in general n data points, okay, and for the n data points we put it in the vectors like this. So we have x1, okay, we have x2, we have xn, where x1, x2 until xn is the vector, consists of some elements like x11, x12 until x1p. So in one vector, okay, consists of p data points, right? And then for the x2 as well, and we have until xn. So the size of these data points is this one, right? N times p data points, okay. And also we consider two classes, right, which denoted by +1 and -1. Okay, now then, other than this, okay, amongst this data point, okay, so this one is called the training data points, okay, training data points. Okay, let's say we have the size of training data point is n times p, right? And then we have another data sets, okay, it's called the test data set, okay. So it's symbolized as the x star, okay, and the same as this, for the x star it consists of x1, x2 until xp. Alright, so how many data then that we have? Because normally under machine learning we split into two, right? Training and test data set. So for the training has n times p data sets. For the test data set we have p. So n times p plus p. Okay, x1 until x2. So n plus 1 times p for in total. Alright. So we aim here to develop the hyperplane that classify correctly the training dataset. So we have the training dataset x1, x2 until xn. So we want to classify that training dataset into two classes. Okay, let's say we have the target of two classes like this. So yi, so this is our the yi here is the target for the positive one. And then we have yi equals to -1, which is the negative, which is another class of the data set. Alright, then the hyperplane that we want to create should or must have two properties. Okay, so the first one as expressed in the equation 5. Okay, so the first one, the hyperplane should be greater than 0. Okay, the second one should be less than 0. Okay, so for the hyperplanes, when we substitute the training data set into the hyperplanes, and then we found that that one is greater than 0 for if this one is for the target yi equals to 1. Okay, whereas for the second condition, where the when we substitute the data set into the hyperplane and then we got is less than 0, for this one is for the target yi is equals to -1. Alright, so now if we substitute these values for the target, okay, if we substitute here into this equation, alright, then just multiply both sides, this one, okay, with 1. So we have yi, we have equation 6, okay, where here yi equals to the hyperplane, okay, is greater than 1 now, not 0 anymore but 1, and then the other one is yi times this one is less than -1. Okay, alright, so once the training data set has been classified correctly by using the appropriate hyperplane, okay, now it's time for us to test the hyperplane by using the observation, by using the test data set, which is symbolized as the x star. You remember that one, right? This one, x1, x2 until xp, and this one all of them is star. Okay, the symbol for the test data set. Okay, again we want to check. Okay, let's say we already create the hyperplanes. Okay, so this one, the function is the f x, right, equals to w transpose times x. Okay, where x is the data set. Okay, and then we substitute the x star into here. Okay, and then we found, after we calculate everything, we found that this one actually is greater than 0. Then we can assign, okay, this kind of data set is classified as the +1. Okay, and then whereas if this one is less than 0, then this is another class, right? So the visualization of that is shown in this figure, right? So this one and this one.